move themify it. Or just do something logo on it.
Okay, today we have I'm going to talk about another model where the idea of this model is to demonstrate situations where you have servers or resources that have different tasks that they need to perform. And then we're going to introduce the idea of transient entities. So far, we've been sort of counting things, and motivated by the last couple of models that we were looking at, where we were able to use containers to do things in the model that we couldn't otherwise do. And it turned out that there were some more things that we would want to do with those models. In particular, the model with reneging gave us, when we used the IDs of the incoming customers, that let us run the model, but it didn't let us estimate some of the measures that we were interested in. And so using these transient entities that we'll talk about, we're able to do that. So, and then I'll give, again, this I think will be the final version of the multiple server queue. And it's called an entity server because it's going to model the multiple server queue, but using these transient entities that we will talk about. Okay, so here's the situation now. So instead of assembling parts or fabricating parts, we are disassembling them. Why? This might be part of either maintenance or repair or even something else. But the idea is that they come in and they have to be disassembled, and then after they're disassembled, they need to be inspected. And then presumably at some point they're going to be either repaired or reassembled, and that would be, if this were embedded in a larger model, then that would be another component, and because presumably those tasks would be taken care of by some other set of resources. The challenge here is the fact that the same group of workers have to do both the disassembly and the inspection. So do you see how this is a little different than the models that we've been looking at so far? I mean, is it clear what the challenge is? Okay, so, and then we have to, it won't come up immediately necessarily, but because there are different tasks to be performed, I'm sorry, yeah, in this model, it's the inspectors are the ones who have to inspect either A or B. So we have one set of workers that are disassembling and another set that are inspecting. But the inspectors have to inspect both A and B, and the question is, if they have a pile of A's or B and B's there available, then which one do they choose? So in a way, this is a little bit of the inverse of the model we had, where we had, it's the inverse of the model where there were two types of servers and the customers preferred one or the other. Now there are essentially two types of customers, each of these components, and now the inspector has to decide which one they're going to do. And that's an assumption that the model makes, which may or may not be consistent with what goes on. If this were something that one was modeling, you would have to go and talk to the people in charge or the people who are actually doing it and say, how do you decide what to work on next if there's more than one possibility? And that's the one that should be implemented. There are, the reason why this first model is going to do the preference one, and then we'll sort of examine that, because it might be that it's just random. If I have an A or B, I'll flip a coin and pick one of those. Or it might be first come, first serve. I'll kind of do them in the order regardless of what kind they are. That would be, all of these are absolutely possible. And the only challenge is that would require using something akin to the transient entities that we're talking about here. So taking a look at this model again, what are the different parameters here? Well, we have two types of workers, the disassembly ones and the inspectors. And then we have times for these things. We have the disassembly times, and then we have the inspection times for A and the inspection times for B. Okay, so again, the parts come in, they have two components. You have to spend some time disassembling them and then inspect them one at a time. Okay, so state variables, motivated by what we've done so far. We have the number of available disassembly workers and the number of available inspection workers. And as you saw in the last written assignment, that's an arbitrary choice. We could have chosen to say the number of busy disassembly workers and the number of busy inspection workers, or some combination of those. Neither one of those are more right than the other. And as I hope you saw, that I asked you to do two different state models of the multiple server queue. Okay, now when we're modeling the parts there, so we have the parts that are in the queue waiting for disassembly, and then we have a set of disassembled A components and disassembled B components. So we need a state variable for each one of those. So just to be sort of clear about what our additional assumptions are, our first assumption is that the inspectors are going to choose A over B if given a choice. We're not going to model the reassembly operation. I mean, presumably, this isn't just sort of an abstract thing where it's not one of these things where you're sort of digging meaningless ditches or something like that. Presumably, this is part of a larger operation. And we're not going to model that in this piece. And in fact, in a lot of times in a larger type of situation, you'll have different parts being captured by different teams. And the second is that the arrival of the parts, we're going to treat that with another component, just as we've done with the arrival process in what we've done so far. Okay. Since I have a bunch of things to get to today, I'm just going to throw the final thing up here and just kind of walk through it. So it looks a bit complicated, but it's not as complicated as you may think, because so who are you going to believe, me or your lying eyes?
My eyes.
Okay, so let's just break this down. Let's forget the bottom part and just look at the top part right here. Structurally, does this look familiar? It ought to, because we've done it lots of times. So structurally, it has the same pattern as our multiple server queue and many of its variants. So a part arrives, and the number of parts in the queue is going to increase by 1. When if there's a disassembly worker available, then you can start the disassembly. So instead of start service, we're starting disassembly. The time is going to be the disassembly time. when we finish, and we'll get to the state transition for that in a bit, but when we finish the disassembly, if there's another part in the queue, then because we will presumably have an available disassembly worker, we can then schedule another start disassembly. Now here's where the difference is. Right here, this is basically the same as our multiple server queue. So forgetting all the others, that's our multiple server queue right there. But then what is it that happens in addition to completing service? So there's more state transitions that occur. And what is it? When we finish disassembling a part, we now have we have 1A and we have 1B. And those are essentially arrivals to each of the respective queues. So we have two queues, two piles of things, one of parts A and one of part B. And when we finish disassembling, then we have one more of those, and that's the state transition. Okay, so that's that piece. Now let's look at this piece right here. And actually, I could have added some events to make it look a little bit more like what we've been doing, but basically that actually together with this, if you look at it, this is also the multiple server queue. That is, we have, okay, this is the piece that's modeling, inspecting a part of type A. So we have one more in the queue of part A. And what this says is that if a worker is available, then we'll start inspecting A, but that's like our start service. And what does that state transition do? It takes away one of our disassembly workers, it takes away one of the part A's from the queue, and schedules an end inspection with a delay of an inspection time for part A. And when you finish, if there's another part A in the queue, then we will start inspecting. Okay, so that piece of it is another multiple server queue where the end disassembly event is like the arrival. Okay, do you see that? Okay, so that's the easy stuff. Now for the tricky stuff. And again, structurally, if we kind of look at this together with our end disassembly event, structurally it's also similar, but what's different are the conditions. Okay, so what we need to do is we need to then kind of go back to the shop and envision what's happening here. So when this event occurs, that means that a disassembly worker has completed disassembling, and we now have a part A and a part B sitting around. Now, because of our assumption that we prefer part A, then we only need to check to see whether a worker is available to schedule beginning inspection of A. So that was the same as the multiple server queue. But here's where it's different here. Because if we have the same condition to schedule the start inspection of a type B, and we only have one worker available to inspect, then we'll schedule both of them at the same time. And the model won't care about that, but the poor guy who's got to do two things at the same time will. And if you've ever been asked to do two things at exactly the same time, that's not the most pleasant thing in the world. I mean, people claim they can multitask, but I mean, if we're doing something like this, you can't do both. Okay, so the condition, though, is basically if there's only one worker available, then we need to make sure that this second inspection of B does not get scheduled. But if there are two workers available, then we can, because one will do A and the other will do B. So that's the condition here. So it says that if there's an inspection worker, if there's more than one available, then we can also schedule a start inspection of type B. And once we do that, it's exactly the same as our multiple server queue, at least going forward. Now, where things get tricky, again, is when we finish that. So when a worker finishes, well, let's kind of go. So basically, everything except for these little cross scheduling things is, you know, as complicated as it seemed at first glance. If we ignore these little cross scheduling edges, then you see that it's really just 3 tweaks of a multiple server queue. Now, the tricky part now comes when we have an inspection worker available. When an inspection worker is available, then what do they do? Well, because of our assumption that they will prefer type A, then all the worker needs to check to see, is there a part A available? And if there is, they'll schedule a start inspection on that, because if there's an A available, then that's all they need to know, because that's the preferred one. Okay, but what if an A isn't available? Then what? Well, he's supposed to inspect a B. So how can we capture that? Well, first by scheduling a start inspection of type B with the condition that there are no type A's available and there's a type B available. If that condition is met when we finish inspecting an A, then that worker will turn and start inspecting a B. And how do you do that? You schedule a start inspecting B. And exactly the same criteria apply when we finish inspecting a part B. So the fact that we just finished a B is irrelevant to what we do next. Because again, because we prefer a type A, we'll always schedule a type A if one's available. But if there's no type A and there's a type B, then we can begin inspecting a B. Okay, so now, basically, when you see sort of a model that's kind of thrown down like this, and it looks a little bit like, you know, your eyes glazing over and everything, that's a natural thing. But knowing what you know now, you can kind of inspect it and identify some of these patterns. And this multiple server queue pattern is one that arises again and again in various forms. And so recognizing that, you can figure out what this is doing. Now, if you had to create this, then you would just kind of do exactly the same thing that we've done so far. You define your state variables, you could just identify all of these events without the scheduling, and then, you know, by analogy to, you know, like when you take a test, do you start with question 1 and then do question 2 and question 3? I mean, that's the worst strategy.
I usually do that till I hit a block and start skipping ahead, looking for other easier ones, and I circle back to the hard ones.
Exactly. I mean, that's the optimal strategy for a given level of studying. That will maximize your score. Same thing when you're doing the modeling. In other words, having identified all the state transitions, the optimal way to then figure out the scheduling would be to pick off the ones that are easy. So like all of this at the top it would just be very straightforward. The part of inspecting A would be likewise straightforward in itself, and then the challenging one would be figuring out what's going on with B, and then realizing that we had these other scheduling possibilities. Now, for something like this, now notice for whatever reason, instead of arrival event, the event was called part arrival. So what do you do if there's an event that you want to trigger, and the only thing wrong, the only disparity is just the name. So we have an arrival process. Remember our arrival process, and let's say we wanted to drive this with an arrival process. So we got this kind of we got this in our library, as it were. Do you see why an arrival process is not going to work with this? Because this will create arrival events, but this component wants a part arrival event. So how do we fix that? We fix that with something called an adapter. An adapter does exactly what you might think. Like, in other words, we have an event that matches in everything except name. And it has to match the argument. But if the only disparity is the name, then we can simply create an adapter. And the adapter in this case would adapt the arrival event to the part arrival event. And so the way this works is that whenever an arrival event occurs in the arrival process, the adapter says, okay, I'm gonna tell this listening component that it wasn't an arrival event, it was in fact a part arrival event. And then that will in turn trigger this event, which will then set everything else off. Now, one of the things that's important to do is to kind of say, well, we talk to the people in the shop, and they say, well, if I've just inspected a type A, then I'd rather just kind of do another A instead of switch. So they'd rather fight than switch. And if you're into kind of classic ads, you might ask your grandparents about that. Okay, so how can we capture that? Okay, so that's a different rule, and it would require a different model. But the only place where it would be different is just in these events right here. I mean, it doesn't affect the top part, it only affects that piece right there. And how would it affect it? Well, oh, I'm sorry, yeah. This was the opposite. They switch. So, I'm sorry. I'll leave it as an exercise to figure out how you would do it if they wanted to stay the same. But now we say we want to switch. So what that means is that if I finish inspecting an A, I'd rather inspect a B. Okay, why would one prefer that? Well, because presumably in the reassembly piece, if I have parts that have finished inspection, then they need to be matched up. If I always prefer part A, then what's going to happen? I'm going to have a big pile of part A and no Bs, and then I won't be able to kind of match them up because there'll be a mismatch. Whereas the switching means that I'll roughly have one of each, roughly. So the way to capture that is that if I finish an A, then I would actually prefer to schedule a B. So all I need to do is check if there's a B, and I'll schedule a start on A only if no B is available and an A is available. And likewise, if I finish inspecting a B and there's an A available, I will do that. But if there's no A but a B, then I'll do that. Okay, what's another rule for this? Well, maybe choose the larger queue. Like as things are going on, you again have two piles of these components. And so instead of switching or following any other rule like that, I'll look and see which one is the bigger pile. I'll take the bigger pile and I'll choose one of those. How can we do that? Well, when we finish inspecting an A, then we're going to start inspecting an A if there is an A, and let's say that the A is at least as big as the Q of B. In other words, if A is at least as big as B. Otherwise, if the Q for B is bigger, then we're going to switch. And likewise, if we finish inspecting a B, if the B Q is bigger than the A Q, and in fact it is bigger than 0, because see, if they're both 0, this will be true, but we need to have at least one, then we'll do a B. But if the A Q is bigger, then we'll schedule an inspection on A. Okay, the lesson here is that none of these things are laws of nature. Everything that goes into the model is something that needs to, at least to the degree to which the model is abstracting your system, capture what the rules of the system are, how the system operates, again, to a level of abstraction. And so what we've seen is that for the same system, there are 3 alternate possible rules. Which one should we do? We should do the one that they actually do in the system we're modeling. And some questions which sometimes come up are things like, well, which would be the better rule? Maybe we're doing one of these, but is that the best one? So what a model like this could do is it could, once you establish which measures you would evaluate your system on, you could run the 3 different rules and see which one performs better. Based upon what? Based upon the measures that you would be interested in, such as the average number in the queue, utilizations, things like that. For something like this, you'd mostly be interested maybe in the total number of sort of A's and B's together that are marching out that you can send to the next place. Okay, transient entities, and there's there's a section in the reading that talks about this, so read that to just be clear on this. So the idea of transient entities is we think of them as objects that are going to represent the things in the system. And those things can be either like people things or machine things or part things. And historically, this is something which came up in simulation modeling, and this is the terminology that they used. It actually predates what we know as object-oriented programming here. Actually, the very first object-oriented language was a simulation language called Simula. And entity is the language that is used in simulation, and so that's the language we're going to use. They're basically objects. And so they call the instance variables attributes. And our entities also can have methods, so just think objects. So an attribute is like an instance variable. So the entities that are built in that we can assume we already have will have these three attributes: a name, a creation time, and a timestamp. And then implicit attributes would be the age and the elapsed time. So, and then the two methods that we have kind of out of the box are one is called stamp time, and what that's going to do is that's going to set, it's not a setter really, but what it does is it literally sets the time, sets the value of timestamp to the value of sim time. Basically, that's like, you know, when you go in a parking garage and, you know, you get your ticket, it's stamped with the time. That's basically what it does. And so, but you have the ability to do that at any event that you want. So at any event, and we'll see how that works, if we call stamp time, that will cause the entity to remember what time that event occurred for it. And if you think back to when you were trying to determine, say, the delay in the queue, if you remember doing that by hand, like what was some of the things that you needed to do? We'll go back and say, when did this customer arrive? So if we now have one of these entities around at the arrival event, and we call stamp time, then their timestamp is going to be the time at which they showed up at that arrival event. And then just for convenience, we can get the elapsed time, which is going to be the time between the current simulated time and the timestamp. And it should be clear that this is always going to be a non-negative value, because because time goes forward. Never, as we've seen, there are sometimes zero delay events, event scheduling with zero delay, but so that's why it can be non-negative. Okay, so if you remember our simplified UML class diagram, so basically we have the name, creation time, and timestamp. It also has one of these ID things, which is done in the same manner that we did last quarter, where you have this static variable that gets incremented for. So each entity will have a unique ID. Sometimes that's necessary when we have it on a sorted set. And so we can get the age. So the age is the creation time never changes. That's going to be basically a final variable. And the age is going to be what? It's going to be the difference between now and when it was instantiated. Whereas the elapsed time is the difference between now and when we last stamped the time. And then if we call stamp time on it, that will cause the timestamp to be set to the current time. Okay, so an example of using this in an event graph context is the entity, we're calling it entity server component. So this is going to be our final version, at least from a design standpoint, of the multiple server queue. So I have the same parameters, number of servers and service times. Again, we're going to be driving it with an arrival process or any component that produces arrival events. We have our usual suspect of the number of available servers. And now, if you remember, previously we had a container of times, but now we're going to have a container of entities. So what's going to happen is our component an arrival is going to be arrival of an entity, and that entity is going to be put into this container that's going to hold them. So our queue is going to be, now we're going to have, the model is going to have individual elements representing each individual customer. And as before, the things that we want are the delay in the queue and the time in the system. And just as before, those are tally state variables, and so they don't have an initial value because they don't really exist until the event corresponding to them shows up. So here's what that component looks like. And again, just to kind of keep things a little bit less messy, there's a little bit of a shorthand for this. So again, the run event, we're going to clear the queue, initialize our number of available servers, and the other two are not, these are actually somewhat optional, but. Okay, so now our arrival event is going to have an argument, which is going to be an entity. So knowing that that's an entity, what we're going to do is going to stamp its time, and what that's going to do is cause that entity to remember when it arrived. And hopefully you can kind of see that since we now remember when we arrived, we can now get the elapsed time is going to be the time between when they arrived and some other event that's of interest. Such as, so we add it to the queue. Just as before, if there's an available server, we're going to schedule a start service. Now let's look at our start service state transition. We're going to pop off the first guy from the queue, and that gives us an entity. So we, again, as before, we lose one of our available servers, but now the delay in the queue is the elapsed time of this entity. So because the entity remembered when it showed up at the arrival event, the elapsed time is the time between when the arrival event occurred and the start service occurred, but for that entity. And now in order to get the time in the system, we're going to schedule our end service as before with a delay of a service time, but now we're going to pass that entity to the end service event that will receive it as an argument. So we will give back one of our servers, but now the time in the system is also the elapsed time. In other words, the time between this entity ended its service and when that entity had arrived. And so even in a non-first in, first out system, if we have more than one server, remember that customers could pass each other. And if that's the case, because we are passing this entity to the end service event, when the end service event occurs, its argument is the entity that completed service. And so the elapsed time is the time in the system for that entity. And so this will allow us to tally both the delays in the queue and the time in the system. And since we have sort of, the full name would be get elapsed time, just as shorthand, it's just being represented this way, just with an understanding of that. Okay, so now how do we drive this? Again, the arrival process by itself can't drive this, so we need essentially like an entity arrival process. So conceptually, it would look like this, where we have arrivals that are scheduling each other, but then now the arrival event is going to instantiate a new entity and schedule an arrival event passing it as the argument. And that will allow us to hear an arrival event with an entity as its argument. And of course, the lazy way is to simply subclass our arrival process. And so our entity arrival process will simply have an arrival. It'll kind of call the superclass one, but instantiate the entity and schedule the arrival. And so this way, our entity arrival process can drive our entity server by having the entity server listen to the entity arrival process. So how does that work? This will produce a stream of arrival events that have an entity as its argument. The entity server component has an arrival event with an entity as its argument. It will hear that and resonate with it. Okay, so now how does, well, as it happens, hopefully, let's see, hopefully this will, okay, if you pull the class code, okay, what did you do to me? You put, it always does this. Where the heck are you're saying you're not there? No internet connection. Come on. There we are. Okay. All right, let's try this again. Let's pull. And what will happen is, here's our entity server. Hopefully I did this right. So here's our total number of servers, that's K. Here's our service time generator, that's T, the service times. Number of available servers, that's S. Okay, so now our Q is going to be a sorted set containing entities. And as you can see, now entity is a very popular name, so you got to be careful about that if you are using one of these, and you will shortly, that you import the SimKit entity one, not one of the other ones. Like if I kind of try to fix the imports, you will notice that there are a bunch of other possibilities, but I want the SimKit one. Okay, and then the delays in queue, etc. So we have our constructor, our master constructor, which has all the parameters in it. Our zero argument constructor. Now here's the tricky part of implementing situations where you have a container as a state variable. You need to instantiate it somewhere. And so the best place to instantiate it in this case is in the zero argument constructor, because that guarantees that it'll be instantiated no matter whether you instantiate it with the zero argument constructor, but you want to make sure that that's also the case for the master constructor. And so what you do is you call this. Remember that you either call this or super, and if we call this, then that means that the Q state variable will always be instantiated. And we're instantiating it as a sorted set in this case, because entities are sorted by their timestamps. Okay, the reset method, again, this is pretty much the same. We clear. Our run event is only going to fire property changes because we're going to be listening to our other one. Okay, so now here's if you remember, we kind of, well, first thing is we stamp the time of the entity. So the next entity is the argument of the arrival event. We stamp its time, because now it's going to remember what that is, and now we need to put it on the queue. And so we do the same little dance. We get the old value of the queue, we add the entity, and then we fire the property change. But there's an extra wrinkle when we have one of these. And that extra wrinkle is that we, in order to maintain, at least have a certain modicum of encapsulation, our getter method, where is it? Our getter method, if you remember, for a situation like this, where's our getter? Yeah, so our getter method returns a shallow copy of our container, and that's important. So when we get that, we're getting a shallow copy, we add it, and then we fire the property change just as before. Same criterion as the simple server. And okay, so now in order to Historically, when we have a data structure, we can, the term pop is something that we says just pop the first guy off. Unfortunately, Java in their wisdom did not call it pop, and they don't give us a pop. So we got to do pop some other way. So the other way is, again, we want to, for the old value, we want to save the old value. So what we need to do is first we need to just get the first guy and then remove that guy from the queue. So these two together do pop. It would have been nice if they did a pop, but they didn't. And so we got to do this. Now the delay in the queue is simply the elapsed time of this customer we just popped off. Then just as this is the same as the simple server. And now, okay, so now we need to schedule the end service, but passing it an argument. And how do we pass an argument? The arguments are always going to be the last elements of the wait delay call. So the first argument is the name of the event. The second is either the time or a random variable that will generate the time. And then if there's anything after that, if there's a priority, then that will be in here. But here we're passing it the customer as an argument. So you do have to be a little careful about that. But now here our end service has an entity which is a customer as its argument. So the time in the system is just the elapsed time now. Since we stamped it at the arrival event, the elapsed is the time it's been in the system. And everything else is more or less the same. All right, let's look at our entity arrival process. Again, that's simply extending the arrival process as before. We write the two constructors, and now our doArrival event, which should have an override method or override annotation. So we call the super to make sure that they keep coming. We instantiate an entity, and then we schedule an arrival event with 0 time, passing it this next entity. So how do you run that? Well, again, and you can. This is if you do a poll, you'll get all this. And so what? These are actually the same parameters as for the simple server. Only now we have an entity arrival process. We have now to collect the delays in queue and the time in the system. We had a simple stats time varying, and now we have a simple stats tally. The third stat is something called a collection size time varying stats. And what that does is that listens for a state, which is a collection, which a sorted set is a collection, and simply does a time varying stat of the size of that, just as the name describes. And so we're running short on time, and I can continue this tomorrow, but I encourage you to sort of take a look at this. And so what I've done here is I've also, now that we can explicitly get the delay, compute the delay in the queue and the time in the system, we can sort of check Little's formula. And that's basically what this does. So we're running it for, again, just same parameters as before. We'll run it for 100,000 time units. Have the same number of arrivals and customers served. So the average number in the queue and utilization, and we have there. We've also computed the average arrival rate. Remember, that's just the number of arrivals divided by the end of sim time. Now, because we explicitly tallied the delay in the queue and the time in the system, we can just simply report those as the mean. But because we also have the time averages of the number in the queue and also the number in the system with a little bit of effort, we can use Little's formula to compute the average delay in the queue and the average time in the system. And we see that they're actually very close. They are not exactly the same. They are not the same because we can see that right here. We see that there have been 475 arrivals and only 472 served. That means that there are 3 still in the system. And because we have 2 servers, that means that at this point both servers are busy and there's 1 in the queue. So the queue is not empty and the system is not empty. So that means that Little's formula is not going to exactly hold, but it holds pretty close. So the percent error is like 0.0015%. And again, that's a percentage because it was multiplied, the absolute difference was multiplied by 100. So that's pretty damn close. And if you look at this, the delay in the queue differs only in the 4th decimal place, and the average time in the system differs only in the 3rd decimal place. So this doesn't prove anything, but it's an indication that Little's formula, if you run your system long enough, is going to be approximately true. And we're able to check that with our system here. Okay.